So let's move on to the next talk, given by Luis Diego Pinto from EAPS INAF about the characterization of vapor, water, emission from polar lunar craters.
So good morning to everyone. Thanks the organizer for giving me the opportunity to introduce my work. I'm Luis Diego Pinto from the Astrophysics and Planetology Institute of Rome, and today I'm going to introduce you a numerical study we are developing in order to study the water ice and dust deposition on the polar lunar surface regions due to a cometary impact event. Nowadays, it's well understood that there is the presence of ice, even long-term presence of ice in the polar region of the Moon, and especially we want to focus our attention to the internal regions of a crater, which may have the right thermal condition for the ice to last even several million of years. So it is very important to focus the behavior of eventually the gas or the dust, which may bring the ice to condense on these peculiar superficial zones. In particular, it is the thermal transport modelization inside the surface, inside the craters, may play a crucial role in order to determining the possibility to water ice vapor to condense on the surface. A cometary impact basically releases immediately water vapor due to the huge thermal energy released after the impact, and so we have a short term atmosphere which may be composed by water, ice vapor, and eventually dust. The condensation process of the water vapor on the surface may depend on the local pressure and even on the thermal surface conditions. So basically, our model aims to use two numerical schemes to perform the study. One is the mesh finite element method, which will allow us to perform a correct and detailed study of the temperature of the surface of the polar region of a moon. Even we may use this temperature as the border and condition to support the study of the hydrodynamical evolution of the gas component, which is studied by another scheme, and this is the part to which I want to focus with my presentation today, which is a Lagrangian smoothed particle hydrodynamical scheme, which allows us to investigate the hydrodynamical evolution of the water vapor and also the interaction of the vapor with eventually the refractory dust component. The final goal is, of course, to determine in details the rate of condensation of the ice, of the water ice on the ground. And so just a brief introduction about the SPH scheme. SPH scheme is a Lagrangian method used to study the hydrodynamical and dynamical evolution of a gas. Basically, it consists in an ensemble of particles used to sample the density distribution of a fluid or whatever fluid, and each point contains the average local hydrodynamical properties of the gas, as temperature, pressure, and density, and even the velocity field. The particles are free-moving particles, and so are well suited to sample whatever shape of gas, and also whatever shape of border conditions. In this case, the border condition used by our simulation are given by only the rim of the crater. So basically, today I'm going to show you a simple approach we use it to simulate this phenomenon. So we use three components of matter. One is given by the water vapor released by a comet after the impact on the surface. The other component is given by some particle representing the water ice, and another component is given by some particles representing dust made of refractory matter. Here we use a lot of approximation, especially that there is not the self-gravity, so the gas feels just the moon gravity. We have also a drag force, which plays an important role because it makes the gas interact with either the ice particle, either the dust particles. And we use simple condition to schematize the condensation or the sublimation of the water ice. Water ice condense or vice versa. The water ice may sublimate, converting into gas according to the ratio of the local gas pressure and the saturation pressure, plus some thermal condition given by a simple surface model, which we use here to schematize a periodical surface thermal model, rather than the complex mesh grid scheme we aim to use. And so I'm going to show you the initial condition of a simulation, an example of test we performed by schematizing the gas and the dust as an initial hemisphere made by 50% in mass of dust particles and 50% in mass of SPH gas particles. This hemisphere represents the direct consequence of the impact of the comet, which we avoid to simulate directly. And we also place an irregular border condition given by the rim of the crater, placed 150 kilometers in linear distance between from the barycenter of the gas system, and we start our simulation by simply letting evolve the system according to the SPH equation. Now I try to show you a movie. I hope it starts. So we can see both the two components in expansion. Here I'm going to show you in this first movie just the components on the atmosphere. So red dots represent the dust component, while the blue alone represent the column density of the gas distribution. So we can see the drag interaction between gas and dust let the gas be transported even close to the crater. And in this second movie, we just can see the ice deposited on the ground, which is shown by the blue dots, together with the refractory dust component deposited on the ground. As we can see, there is a non-negligible amount of matter deposited inside the crater. And here we can see with the blue lines the ice deposited on the moon. The dotted line represents the ice deposited inside the crater, while the red line represents the dust component deposited on the ground. As we can see, there is a non-negligible percentage of ice which may be deposited on the ground. Of course, this is a first zero study, just to explore the possibility, the concrete possibility, which a non-local phenomenon as an impact of a comet on the surface, far from a crater, may cause, may bring to some ice structure formation inside a crater. But of course, this is just the beginning of our work. I wanted to show you just the first zero investigation. So thank you very much for your attention.
Sorry, is there a quick question for Diego? I was just wondering if you can have an estimation, sorry, of how much water could be then retained, or is that further work you are going to do after that?
We didn't perform the specific investigation about this kind of results, since if I understood the question, you wanted to ask if the ice may last.
Stay. Yes.
This is actually it represents a crucial result, which may go beyond our goal, simply because the time scale of ice lasting could be very long with respect to the time scale of our simulation. So at the moment we will not able to perform such study, just because of the long difference of time scales. But when we will reach a more detailed capability to study the thermal evolution of the surface with the mesh grid scheme, probably we could perform a study to understand if some ice would sublimate in short time scale from the surface after the condensation, or maybe if the ice would last for a short time scale. But okay, since the time scale could be even 1 million of years or longer, yeah, for certain craters, I think we need a separate investigation to,
yeah, of course,
to understand it.
Great, thank you.